Hey everyone, and welcome back to The Explainer. I am absolutely thrilled you're joining us today because we're putting together the ultimate study guide on a piece of tech you literally use every single day. We're going to rigorously break down the architecture of the RNN Transducer, or RNN-T for short. It's the powerhouse behind modern streaming automatic speech recognition. If you've ever wondered how your devices can perfectly transcribe your voice in real time without skipping a beat, well, you're in exactly the right place.
I want you to think about this for just a second. Why exactly does your phone's dictation instantly know that the letter Q is almost always followed by U, and it does it without pausing to think or looking it up after you finish speaking? I mean, it seems super obvious to human ears, right? But for older speech recognition systems, man, this was actually a massive stumbling block. They could hear the audio perfectly, sure, but they totally lacked the internal logic to anticipate what word or letter logically came next. So today, we're looking at the exact architectural shift that completely solved this problem.
Okay, let's dive right into this. Here is our syllabus for today's study session. First, the problem with the older CTC model. Second, meeting the RNN transducer. Third, its 3 core components. Fourth, decoding the 2D lattice. And finally, why it rules streaming.
Starting off with Section 1, the problem with CTC, and exposing the blind spot in older models.
Right, so that fatal flaw we mentioned earlier, it all comes down to a concept called conditional independence. Basically, standard CTC models operate under the assumption that each frame of output is conditionally independent, meaning it completely ignores the previously emitted tokens. Because of this assumption, CTC has zero internal language model. Going back to our Q and U example, a CTC model hears the audio for Q, it outputs Q, but then, when it looks at the very next frame of audio, it's already entirely forgotten about the Q. It's like it has no short-term memory. It can't model that Q is usually followed by U because it literally doesn't look at its own history. It just relies entirely on an external language model kicking in way later to fix its guesses.
Moving on to Section 2. Meet the RNN Transducer. Keeping the good, fixing the bad.
Now, what's really interesting about this slide is seeing exactly what carried over. Older CTC models were actually pretty great in some ways. They were already streamable, meaning they processed audio frames synchronously with incredibly low latency. And they were monotonic, meaning they consumed frames strictly from left to right. But like we said, no internal logic. RNN-T cleverly steps in and retains that awesome streamable, monotonic nature, but it injects the missing puzzle piece, an internal language model. It adds a hard dependency on previous output tokens to vastly improve accuracy, and it does it without sacrificing an ounce of speed.
Okay, Section 3. The 3 core components. Let's look inside the architecture.
So here is the sequential flow of data straight through the RNN-T model. First up, you have the encoder. Just like in the older models, this simply maps the incoming audio into acoustic representations. Pretty standard. Next is the brand new element, the prediction network. This takes those previously emitted tokens we talked about and models the token history. And finally, we have the joiner. Think of the joiner as the brain of the whole operation. It combines the acoustic data from the encoder and the token history from the prediction network, and it uses all that to produce a SoftMax distribution over all possible tokens plus a blank token. And I want to explicitly emphasize something here, guys. This is an encoder, a predictor, and a joiner. This is absolutely not a traditional cross-attention decoder. It's really its own unique animal.
Seriously, if you take away just one single concept from this explainer today, make it this one. The prediction network is the internal language model. Let me just repeat that because it's literally the key to the whole system. The prediction network is the internal language model. By modeling the token history, this one single component is exactly what provides the rich context that CTC so desperately lacked. It is the exact reason your phone instantly knows that the U is coming.
Which brings us to Section 4, decoding the 2D lattice. Let's see how the joiner makes its move. I absolutely love the spatial metaphor the source material uses for this. I want you to imagine the joiner walking across a grid. At every single step along the way, it has to make a choice. If it chooses to emit a token, like a letter or a piece of a word, it moves right on the grid. This means it outputs a token, and crucially, the predictor updates its history. But if it chooses to emit a blank, it moves down on the grid. And moving down means it is officially advancing to the very next frame of audio. Because of this clever right and down movement, RNN-T is actually walking a 2D lattice made of frames by tokens. This is a massive departure from CTC. CTC was totally locked into this restrictive 1D per frame grid limitation. It could only ever output one single token per audio frame.
But because RNN-T's predictor state depends on the tokens emitted so far, and because it can move right multiple times before ever needing to move down, it can actually emit multiple tokens on a single audio frame. Pretty wild, right?
So you might be wondering, how does it actually learn to make the right moves? Well, it all comes down to the loss function. The math here, where loss equals the negative log probability of text given audio, reveals something pretty vital. Just like CDC, RNN-T maps out all the possible token and blank paths through that 2D lattice that could theoretically produce the correct transcript, and it does this using a forward-backward dynamic program. Now, practically speaking, what this means for us is that the system remains totally alignment-free. It doesn't need forced alignment to train successfully at all.
And finally, Section 5, Why it rules streaming, the production standard today.
Let's do a quick review with this ultimate cheat sheet of why RNN-T is basically the king of the hill right now. First, it boasts high accuracy via the internal language model of the predictor network. Second, it's monotonic, so it consumes frames strictly left to right. Third, it is beautifully streamable because it's frame synchronous and spits out text with incredibly low latency right as the audio arrives. And fourth, it's alignment-free. When you pair all these awesome traits with a powerful acoustic encoder, like, say, the causal conformer encoder, you get conformer RNN-T. And that is, without a doubt, the undeniable production standard for streaming ASR today.
So the crucial point here is really highlighted when we compare RNN-T against the other heavy hitter in the machine learning space, attention encoder decoders. Look, attention models give you strong global context, and frankly, they boast the absolute highest offline accuracy. If you have a pre-recorded audio file, attention is amazing, but here's the catch: they cannot stream natively. RNN-T wins the real-time game handily because it perfectly marries native low-latency streaming with a highly accurate internal language model. For live dictation, RNN-T is exactly what you want every single time.
In fact, if you ever find yourself sitting in an engineering interview and someone asks you to define RNN-T, just give them this 60-second elevator pitch. RNN-T is the transducer model. It keeps CTC's monotonic, streamable style, but adds an internal language model. Boom. Hit the nail on the head. You follow that up by explaining the encoder, the prediction network, and the joiner, walking that 2D lattice, and I guarantee you will completely nail the answer. We've seen today just how brilliant RNN-T is at solving that conditional independence problem for real-time streaming. But as we close out today's explainer, I want to leave you with a provocative thought about the future frontier of automatic speech recognition. If attention decoders consistently beat RNN-T in offline accuracy, what technological leap will it take to make them natively streamable? Seriously, think about what happens when the high accuracy of global attention can be delivered with the low latency speed of RNN-T. That is the next great puzzle to solve. Thank you so much for joining me to walk through this fascinating architecture. Keep learning, keep asking those big questions, and I'll see you in the next explainer.